That looks like a fun time.
All right. Hey, everyone. Good afternoon. Let's get started.
What was that you were?
That's Cal 2 stuff.
Oh, hallelujah.
Yeah, no worries. No worries. I'm just
I was sitting there watching you getting real freaking stressed, man. Oh God, I thought we were still working on relative rates, and you're pulling whatever that was out.
No, I'm trying to get some of this code that I've been doing finalized so it looks right, but it looks okay. All right, so no quiz today. I hope that you spent some serious time on related rates over the weekend trying to figure out these problems. It's interesting whenever students come and ask for help on these, just the different approaches, these little subtle differences in the way people label things or what they say is what they want versus what they're given. I mean, everything's kind of unique to the way you look at it, and we can all get to the same answer. It just, you got to make sure everything's, done right. So unfortunately, there's no simple, point A to point B the same way every time, right? There's uniqueness to every one of these, which is why I think students struggle with them. So let's do this one. My plan is to do 2 more. I only have time to do 2 more of these, and we must move on. All right. When I give you a review for your test, which is next week, I will give you a couple of problems on related rates on the review. Here's what I would expect on the exam. I would expect me to give you 3 related rate problems where you choose either 1 or 2 of them. I haven't figured out. We'll see. Maybe it might be just 1 of the 3, might be 2 of the 3, but at least that gives you some flexibility in terms of, hey, I look at that, I have no idea how I'm going to set that up. At least there's a few others to choose from so that you can at least demonstrate that you understand the basic concept. All right, here we go. The conical cup problem. So we have a conical cup. So a conical cup is a cup that looks like a cone, like this. All right. It is 4 inches tall, 6 inches wide. So 4 inches tall, 6 inches at the top. Water is being poured into the cup at a constant rate of 2 pi cubic inches per second. How fast is the water level rising when the water is 1 inch from the top of the cup? So you have to imagine this is an empty cup. You start pouring water into it at a constant rate. The water is going to start coming up the cup. But because the cup is very narrow at the bottom, in the beginning, the water level is going to rise pretty rapidly. But as the cup spreads out, right, because the water's coming in at a constant rate, it should be slower as it gets to the top. That makes sense to everyone? I have an animation of it. Here. It doesn't help you solve the problem, but I have it where the computer is going to basically start filling this thing up at a constant rate, and just watch what happens to the level of the water. See, in the beginning, it popped up really fast, and now it's just slowly coming up that cup. Slow, 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 slow. Eventually it will overfill, right? But it takes longer to get higher because the cup is spreading out. So y'all okay with the idea here? We've got water in a cup.
Yeah, it's not a difficult concept.
Seem reasonable?
Yeah.
So time to draw some pictures. I have a cup. Let me do it this way. I have a cup, conical cup. And here's some things I know about this cup. It is 4 inches tall and 6 inches wide, right? Now, when I'm reading this, I'm just trying to put information in here. Like, what am I given? What do I want? Sometimes it's easier just to look at what you want first. How fast is the water level rising, right? How fast? So I have to visualize the water in the cup coming up, right? And so the water level is how high or how deep that water is. I need that in my picture. So I have to make the distinction that I'm not talking about the cup here. I'm not talking about the cup. I'm talking about the water within the cup, right? So I need to draw my water that is at some height in the general picture. It could be anywhere, but I'm just going to put it there. And so I'm going to label this distance from here to here and call it H for the height of that water. So if the question is asking how fast is the water level rising, then I want to know how fast H is changing with respect to time. So that means I want dH dt. Now there is a moment in time where I want that. It says how fast is the water level rising when the water is 1 inch from the top. 1 inch from the top. So what do I know? If it's 1 inch from the top, let me draw that picture over here. This is the exact moment in time. The water level is just 1 inch from the top up there. Then can you tell me how deep that water is then?
Should be 3 inches.
1 minus H or 3.
3, right? 3. At the exact moment, I can say H is 3 because the cup is 4 inches tall. And if I'm 1 inch from the top, my H must be 3. So I want to know how fast that height's changing at exactly the moment that H is 3. So that's what I want. Now, what about something I'm given? A conical cup.
So that 6 inches wide, that's basically circumference of the top, right?
It's diameter of the top. It's from one edge.
Yeah,
to
diameter, yeah.
It's the diameter across.
So
water is being poured into the cup at a constant rate, 2 pi cubic inches a second. So you should be thinking 2 pi cubic inches a second. This is a derivative, right? This is a rate that something is changing.
That'd be
the rate at
dH dx, right?
That would be the rate of 2 pi cubic inches is a measurement of volume, right?
Mm-hmm.
So this is the rate of change of the volume of the water, right? Not the volume of the cup, the volume of the water with respect to time. So I'm given dV dt equals 2 pi. You know, you can put the units if you want. You don't have to. Cubic inches a second doesn't hurt. I can put this here. This is inches, right? So the question becomes, is this enough? Do I have everything? Have I missed anything up here? I think I've used everything. I need to connect the two variables together, V and H, right? The volume of the water to the height of the water. Any formula out there that I can come up with that connects volume to height, and we're talking about a cone here. So this is where I'd want to go and probably look at my formula sheets, right? And way up here, we have a cone. There it is. And the volume of a cone is 1/3 pi r squared h. 1/3 pi r squared h. So I'm going to use that. I'm going to put a volume formula down here that the volume of the water, right? The volume of the water should be 1/3 pi r squared h. Now I keep getting this question, and I'm kind of upset with myself for not really like stressing this to you to the point that you're sick of hearing it. Whenever you have your equation, you are not allowed to plug anything in for any of your variables that are actually in motion during the problem. So with the water level is changing, right? The water level is changing. And therefore, I cannot replace H with 3, not until after the derivative. So I think I say this in here, somewhere in here. Thought I did. I think it's in the notes. Let me look at the notes real quick. Pretty sure it's in the notes. Go back up here. There was a set of steps way back in the beginning.
So there was like one problem on the homework where you did kind of like plug it in before you took derivative over. Is that because it was like constant, or I can't remember what you said it was?
It has to be something that never changes. Like the problem we did, remember with the airplane flying over, the altitude of the airplane never changed. It never changed. It was always the same. That you can keep in your formula as whatever it is. But here, look, our formula right now, come on, hold on. Doesn't want to scroll. There we go. Our formula right now is that the volume is equal to 1/3 pi r squared h. Nothing in here is constant. You cannot tell me that the height is 4. We're not talking about the cup. We're talking about the water, right? That's important. And you can't tell me that h is 3 because the water is coming up the cup. Okay, so you can't fix h to be 3. So never replace a variable with a constant until after the implicit differentiation, unless that is constant throughout the whole problem, even while things are in motion. Understand?
What about R?
Yeah, so, okay, we've got an equation, right? Here we go. We've got this equation, it has the volume of any cone. So we're happy about the equation because it has V in it, and dV dt is something I know. So I know if I differentiate this, I'm going to get a dV dt because of chain rule. And then I also have an H in this, so I know when I differentiate, I'm going to get a dH dt, which is great because that's what I'm looking for, right? But there's a problem. There's an R in here. And that means if I differentiate, I'm going to get a dr dt, right? A dr dt, which I have no, I have no information about dr dt, right? It wasn't given, right? It's not something I want. It's almost like a variable that I wish wasn't there. Do y'all agree? Like I really wish R wasn't there, because if R wasn't there, then I would only have H and V, and then I'd be happy and everything would work out nice, right? So here's the critical step. This is the critical step of this problem, is that you really don't like the R. But this cone, this water that lives inside this other cone, if we start messing with it geometrically, we might be able to find a relationship between R and H that will allow us to eliminate R from the equation. Okay, so what do I mean? Let's take a look. I need a new page for this. Let's take a look at that cone, right? And the water inside of it at some arbitrary level. Imagine that you could come in here and cut right down the center of the cone. And imagine the water wouldn't pour out, okay? So you cut down the center of the cone and you open it up and you look at it from the side. If you do that, here's what you're gonna see. You're going to see a triangle like this, and you're going to see your water level in here like this. So what I've done is I've come through with like this imaginary knife, and I've cut through right through the middle, right? Just sliced it right down the center and opened it up. And I'm looking at what we would call a cross section of this. Okay. Now, if I look at this cross section, I can start to see, if I go right down the center of it like this, I can see a couple of triangles, right? And if I start labeling things, this right here is R. This distance from here to here is the actual radius of the water part, right? That little, just that little distance from here to here is the radius of the water. And the distance from here to here, well, that's the height of the water, isn't it? But that all lives in this bigger triangle. So what I'm going to do now, I have to kind of pull this apart to hopefully make it easy to look at. I'm going to just not even look at the left side of this, just the right side. I have a big triangle like this. Then I have this smaller triangle inside of it like this. I know this is H. I know this is R. But see, the bigger part, the bigger triangle, that's fixed. That never changes. So this is 3 because all the way across was 6, wasn't it? So that's 3. And this entire length here is 4. And so what I have now are similar triangles. So this requires you remember something from geometry somewhere in the past. And if you don't, it's okay. I'm going to go through it again. The way similar triangles works is this. Let's say you have a triangle. Doesn't matter what the triangle looks. Oh shit, that's terrible. Let's say you have a triangle, right? And let's say it has this angle. I don't know if y'all seen that before. I put a little angle here and a dash through it. That means that's like angle 1. Let's say this is angle 2, and then this is angle 3, right? Let's say I have another triangle that's not this one, but it's different. That's maybe a little bit bigger than that one, but it has the same angle measures. These angles are the same. So they match up, right? They have the same angles. If you ever have this, these are called similar triangles, and they have a very, very nice property. If we label this side little a, little b, little c, and these sides, capital A, capital B, capital C, then similar triangles, the property, what you have with similar triangles is that the ratio of any corresponding sides must be equal. Okay, so what do I mean? I mean, if I take this A and divide it by that A, little a over big A, that should be equal to any other side on the little triangle divided by its corresponding side on the other triangle. So I can say that that's equal to little c over capital C. And that works for any corresponding sides. So something else I could write little a over big A equals little b over big B. Or you could write, there's other things you can do. You can do two sides on the same triangle. So if I say like little a over little b, little a over little b must be congruent to capital A over capital B. That's what similar triangle is all about. Does that make sense? We're not going to prove it to you, but this is what similar triangles tells you. I'm not going to get into any more depth into this. For similar triangles, though, you have to have congruent sides, congruent angles, equal angles. So all the angles have to correspond to each other, and then you can set up ratios of all the sides, and they should be equal to one another. So I'm about to use that because what I have here in this picture is I have a big triangle that looks like this. It's got 3 here and 4 here. I know this is a right angle, 90 degrees. And whatever this angle is, I'll call it whatever. And then whatever this angle is, I'll call it that, right? That's what this big red triangle is. Then I have this smaller triangle inside of it that looks like this. But I know that this is also a right angle, right? That's 90 degrees. And both of these triangles share this angle right here. They both have this angle. So I can tell you that this angle has to be the same as this one. And so if they both have a 90, right, and they both have this same angle, that means this last angle has to be the same too. These two have to be the same. And so they are congruent. They are similar triangles. You with me? So now this is R and this is H. So now I am free to set up a ratio however I want. I can do 3 divided by 4 equals R over H. I could do 3 divided by R equals 4 over H. I could say R over 3 equals H over 4. It just has to be corresponding. What you can't do is this, 3 over H equals R over 4. They have to be corresponding sides. So I'm going to do it however I want. I'm going to decide to do R over 3. Okay, I'm going to do R over 3 equals H over 4. And now I have a relationship between R and H, right? And I could multiply both sides by 3. And I get basically that R is always 3/4 of the height. The radius of the water is always 3/4 of the height. Just multiply both sides by 3. And this should be a true relationship as long as the water is inside that cone that we're talking about, right? The one that's 4 high and 6 wide. As long as that's the cone we're talking about, this should be the relationship. And this is great because now I have a way of replacing R in that formula earlier with something that has H instead. So I go back. And now what I put is this. Volume equals 1/3 pi. The radius is now being replaced with something times H. Replacing radius with 3/4 the height. If you don't slice that cone in half and look at the cross section and do similar triangles, you don't have any way of getting rid of R. And if you can't get rid of R, you're going to have a dRdt. And if you have a dRdt, you're stuck because you don't know anything about it. So I'm not going to differentiate yet. I'm gonna continue to simplify this algebraically. I'm going to go ahead and square this. So when I square this, I square each one. So I get 9/16 H squared, but then I still have an H. And let me kind of simplify this. 3 goes in here 3 times. I think I have a final version of the volume formula. Volume is, let's see, I still have a 16 on the bottom, so I'm going to put 1/16 pi H cubed. There it is. I can put those H's together, right? H cubed. There we go. For this particular cone, this particular water in this particular cone, that is the relationship between the volume of the cone, the volume of the water in the cone and the height of the water in the cone. And now I differentiate. So I take the derivative on the left side, dv dt, right? On the right.
Wouldn't it be 3/16 pi H?
Oh, sorry. Yes, thank you. Y'all were all looking.
Okay,
I
just
canceled
wanted
the
to
3
make
and
sure.
I forgot there was a 3 on top. Oops. Thank you. That's a 3. I forgot that 3 right there. That's why I'm so glad y'all keep your cameras on, because I look at y'all and I can just see it on your face. You're like, All right, dv dt equals, all right, everything here is a constant, right? 3/16 pi, which is going to just come for the ride. And then I just need the derivative of H cubed with chain rule, right? So power rule first, 3H squared times now the derivative of H, dH dt. I really hope that all of you are at a point where this derivative is somewhat trivial in the sense of like the H cubed. Like everyone here should be very comfortable with the idea that derivative of H cubed with respect to T is 3H squared dH dt. Like if you're not there yet, there's ground that you're gonna need to make up quickly. All right, that's it. Now I'm gonna just check this and see if I have everything I need. dv dt, check, that's what I'm given, right? dH dt, that's what I'm looking for. H at the moment in time, now I can plug the H in. See, after the differentiation, this is when you can hold everything constant. And that is the 3, right? So I'm happy about that. So here we go, plug everything in. The left side of this is 2 pi equals 3/16 pi times 3 times the height, which was 3 squared times dH dt. Pi's can be divided out on both sides. what do we have there? 81 over 16 on the left. And then I can multiply both sides by the reciprocal, right? So you should get something like 32 over 81 equals dH dt. I'm just multiplying both sides by 16 over 81. All right, that's it. Whatever that is, we get a decimal on that if we want, but that represents the change in height with respect to time. So my final answer is going to be 32 over 81. What's my units here? This was inches, right? Height is measured in inches and time here was seconds. (32 over 81). Approximately 0.395 inches a second. That's how fast the water's coming up at that exact moment. Okay, let me see. Show construction. There's the picture that shows the similar triangles that you have to see in this problem. And here was the actual answer right there. Yeah, okay. All right, we need to move on. Another question or another problem. Do y'all have any questions on this one? There's one in the homework like this, where they kind of give you something similar to this. They don't give you dV/dt. They give you dR/dt, I believe, if I'm not mistaken. Maddie, you and I were working on that. So I don't remember if it was dR/dt or dH/dt, but anyway, the problem in the homework though, they're telling you that water is being poured in at a constant rate, but it's also leaking out at a constant rate. So the way you should do that problem, I think the easiest way is to ignore the fact that the water is leaking at all and solve the problem. And what you'll find is, let's say at the end of it, you find out that the dV/dt is 10 cubic inches a second. Let's just say that's your answer, 10 cubic inches per second. Then if they tell you that it's leaking out at 2 cubic inches per second, then just your answer is going to be 8 cubic inches per second. Just subtract the 2 from your answer. That's my advice on that problem. And then also on that problem, you have to be careful with units because they give you things, I believe, in meters and centimeters. So anytime you do a problem like this, you need to make sure all your units are the same. So either make everything meters or everything centimeters, but you can't work with them together and get an answer that makes any sense. That reminds me of a short story here. You know, we've had multiple rovers on Mars, right? We've had multiple rovers on Mars, and we even had a drone on Mars, right? Flying around, taking pictures and stuff. Okay, so many, many years ago, before we even put a drone on Mars, one of the first things we did is we sent this probe to Mars, and what it was supposed to do was it was supposed to basically go to Mars and just go into orbit around Mars and try and figure out, like, you know, hey, check that out. That looks like a good place for us to land, you know, just kind of observe Mars, right? So one of the first, I guess, what would you call it? It's kind of, I don't know, a probe, a spaceship. I don't know what it was, but they sent it out, right? And it didn't do that. That's what it was supposed to do. But what it did instead is it just boom. Oh, no, Mars is still there. It just crashed into Mars. That's it. Just boom, we lost it. And they went back and tried to figure out what happened. Well, it turned out that we had computer science people programming the probe to do what it's supposed to do. We had people that were working in Europe, and we had people that were working in the United States. And they were all messing with the code at the same time. And the Europeans were using the metric system, and the Americans were using the imperial system, right? Feet and the versus meters, and that's what did it. It was just a simple conversion, you know. So these little things like that, I mean, in a class like this, it's no big deal, right? But it can cost you if you're not paying attention to that sort of stuff. So, all right, it's all right. It's just our
That
time.
was like a multiple $1 million mistake.
Oh yeah,
That's crazy. Like
millions
all
of
the
dollars
millions
in
of
time,
dollars.
right? That's
All
the
those
lesson.
smart people.
What's that?
Like all those smart people, all that like knowledge, it's just one simple little, like I said, conversion mistake. It's funny.
That's what happens when you use the metric system.
Let's not even go there. All right, so I'm gonna see here. What other problems do I have? So there's a ladder problem. I'm not gonna do it. This is like the cookie cutter staple Cal 1 related rate problem that you could probably go to YouTube and find 100 videos on how to do the ladder problem on related rates. It's too basic, all right? So I'm not gonna do this problem. But I encourage you to go try it yourself, all right? The balloon, I think we did something with the plane. That's close enough. I want to do...
On the homework, there was one that got me a little stuck, and it was like the guy was walking away from a light post, and it was like, it was asking about how quickly his shadow was stretching out as he walked away. Are there any comparable to that we could look at?
Well, I mean, I could do one.
Or is that one I should just go?
That one was difficult.
Yeah,
if I can go through it quickly, then I don't mind covering it, but I can't go through it in the detail that I just did that last one. Like I'm gonna kind of move through this one fast.
Yeah. That one I looked at it and I started on it and I hit a hard lock when I realized I had no idea what formula should be used on it. Just
okay. Yeah, so here's the, I'm not gonna do that one, I'm doing like it. It's almost the same problem. A street light is mounted on top of a 20-foot pole. A 6-foot man walks away from the pole at a speed of 7 feet per second. How fast is his shadow moving along the ground relative to the pole when he is 12 feet from the pole? So in your textbook, they do not say this piece relative to the pole. It's an important piece that's missing in the textbook. I'll explain when we do this. So I'm gonna draw a picture first. I have the ground. I have a 20-foot pole that's got a light on it. So there's light coming out. Then I've got my 6-foot man right here. He's 6 feet tall. He is moving away from the pole at a rate of 7 feet per second. Notice that 7 feet per second is not like, I'm not labeling anything as far as like a side or a length. 7 feet per second is not a length. It's the speed at which something's moving. In fact, you could look at it as this point is moving across the ground to the right at that speed. So I've got this picture. His shadow is basically going to be on the ground over here, right? If this is his head and his arms, then his head's going to be on the ground and then his arms, and there you go, like that, right? That's his shadow. So the question is, how fast is his shadow moving along the ground? So if I were to take a point, let's say the tip of his head there, that shadow should be moving this way, right? As he moves out, that point should move further away. And we want to know how fast it's moving. The confusing part is this. Are you talking about how fast is it moving relative to him or relative to the pole? Because he's moving too, right? So if he's moving and he's looking at his shadow is moving away from him, right? You could ask, what's that speed relative to him? Or you could say, oh, you're just standing at the pole watching all this happen, and you're asking how fast is that shadow moving away from you standing at the pole? Two different answers to those questions. So the book doesn't state it. I would always state it in a problem to make sure it's clear. We want to do this relative to the pole. All right? Understand? So I'm going to write down what I'm given and what I want. So given, what do I want? All right, I'm going to start with what I want. I want to know how fast his shadow is moving along the ground relative to the pole. Well, here's his shadow. I'm going to measure the distance from here to the pole, and I'm going to call that X, okay? I want then dx dt. I want to know how fast that's actually moving, right? It's growing. I want to know how fast. I also want to know when he is 12 foot from the pole, right? When he's 12 foot from the pole. Well, I haven't labeled his distance. So let's do the distance from here to here. Let's call that, I don't know, I'll call it M for man, all right? That's the man, that's his distance from the pole. So M equals 12 is when I'm interested in that. I'm given how fast he's walking, right? He walks away from the pole at a certain speed. That's this right here. That's how fast this point's moving, which is also how fast M is growing. So that's dm dt. Y'all just stop me if you have any questions. I know I'm moving quick here.
Can you explain that last part again? Like,
okay, so I called the distance from the pole to the man M. As he moves this way at 7 feet per second, M grows at that same rate, right? M is growing at 7 feet per second. So that's why I put dm dt as 7.
I have a quick question.
Yes.
So if M was shrinking, would that make 7 negative?
Mm-hmm. He was walking towards the pole. Yep. And would it be shrinking? We use -7.
Okay, thank you.
Mm-hmm. All right, there we go. I think that's, at least for now, this is not a bad picture. I need to see, is there a way to connect those two together, M and X?
I'm sorry, did you say that M is negative?
No, no. I was being asked if, well, I don't remember exactly, but if he was moving towards the pole,
Oh,
not
okay.
away from the pole, that dm dt would be -7.
I got you.
All right, so I need some relationship between X and M. And I hope you see the two triangles, right? You see the two triangles? We got a big triangle and we got a small triangle.
Yeah,
Sam?
so
Right triangle,
yeah,
right triangle,
it-
right triangle.
M would be the length of X minus the length of the equivalent on the smaller triangle.
Yeah, X would be this length. From
Ah.
here to here, that's X, right? This is 20, that never changes, right? Now, important. We want this side, that's this side, right? We know that this man is 6 foot tall, that's this, right? The question is, what's this green? Well, M only goes from here to here, right? And then here to all the way here is X. So this should be the difference between the two, shouldn't it? This distance should be whatever this distance is, take away this distance. So this should be X minus M. Now look, this is where I was saying in the beginning of class, little subtleties. Everyone could do this problem a little different, label things a little different, all right? What you want to make sure is that when you come up with that equation, the variables in it better be just what you're given and what you want. If you got extra crap in there, extra variables that you don't have any information about, you're going to get stuck. But here with this similar triangles, I've got X and M and that's it. Everything else is a constant. I can set up a ratio. I'm going to do it this way. I'm going to do this over this. So X over 20 equals this over this. So X minus M over 6. I can cross multiply. I hate saying cross multiply. It's one of my least favorite things to say.
did you do the X over 20? Did you like make that equation because the whole congruent angle thing from
Yes.
triangles? Or?
Exactly. They both have this same common angle, don't they? Both of them share this angle. And they also both have a 90 in them, which makes this have to be the same, right? If two angles of a triangle are equal, then the third one has to be the same. Well, sorry, yeah. If two corresponding angles are congruent, equal, then the third angles on those triangles have to be the same. So I set up the ratio using similar triangles. And then I'm going to just I'm clearing the fractions. That's actually what I'm doing here. That's why I don't like saying cross multiply. I'm clearing the fractions. And now I actually noticed that I can let's move all my x's to the right. So I get 14x here, and I'm going to move my m to the other side, 20m. And I mean, look, that is probably the most simple equation we've had out of all the problems we've done. That is our relationship between m and x. There it is. It's super simple. Right? There's no crazy, there's no squares, no square roots, no sines, no cosine, just very simple stuff. How you get it is a little complicated, but I'm ready now to differentiate this. So the derivative of the left is 20 dm dt, and the derivative of the right is 14 dx dt.
Oh, that's our proper formula.
Yeah, that's it. Yeah.
Oh, wow. Okay.
Anything that relates m and x together, as long as it's based off of the geometry of the problem, which it is, it's based off the similar triangles.
Yeah. Okay.
There's something very, very profound about our answer, though. I mean, there's something really unique about this that we have not seen. Are we happy to see dm dt? Well, yeah, we know what it is, right? So I'm happy to see this. And dx dt, I actually am looking for, right? But what's missing? What do we not have in our equation that we have over here? M is 12. How does that factor in, right? How does the m being 12? Somehow I'm supposed to be talking about how fast his shadow is moving when he's 12 feet away from the pole. What does the calculus tell us about, what is this telling us about his distance from the pole?
Saying it doesn't actually matter.
It doesn't matter.
The shadow's moving at a constant rate as well.
That's right. Because the formula for dx dt, the thing we're trying, what are we trying to find? Dx dt? Yeah, we're trying to find this, which is how fast the shadow is moving. If you look at this formula for it, nowhere in there is just m by itself, right? M, which is his distance from, well, the distance from the pole to the man, is irrelevant in the formula. That is a profound thing, because if you just think back now, if I gave you this problem again, I said, imagine a pole, right? And a man walking away at a constant rate, and then his shadow, right? If I were to say to you, hey, the speed of his shadow, right? Think about the speed of his shadow on the ground. Do you think that the speed is the same no matter where he is? Like if he's close to the pole, the shadow's moving. If he's 100 feet away, is the shadow moving at the same speed?
Based on what we're seeing here.
You might have an idea, oh yeah, no, I think it's going to speed up as he gets further away. The further away he goes, I mean, think about how long his shadow gets, right? Imagine this guy, here's the pole. Imagine if this guy is way out here, right? Like this. How long is that shadow? That shadow is going to be super long, isn't it? And here in the beginning, the shadow is very short, right? Very, very short little shadow here. Way out here, the shadow is way out there. Understand? So if I'm saying how fast is his shadow moving, you might in your mind think, oh, well, obviously it matters where he is, because the further away he is, the longer the shadow is. The calculus tells us that does not matter, his distance from the pole. And this happens a lot in the real world where things are counterintuitive. They go against what you think would happen. I mean, you're always told trust your instincts, but sometimes you can't. Sometimes you have to settle it with the math. All right, I've gone off topic. Let's go. Let's finish it up. I'm going to take this equation. I'm going to plug things in. dm dt was 7, right? Okay, replace dm dt with 7, divide both sides by 14, and you should get 10. And so it's 10, what was it measured in here? Feet per second. So the man is walking, right, at 7 feet per second away from the pole, and his shadow is moving away from the pole at 10 feet per second. All the time. The shadow is constantly moving around across the ground. If I do the animation, maybe if I do the animation, it'll, let me start it over. Stop. Yeah. Let's just watch Watch the tip of this shadow and let's just see, does it look like it's speeding up or slowing down or staying the same? Let's go. I don't know, to me, it looks pretty constant. Like it's just moving across, right? I don't know. All right.
That's the trip. I was legit not expecting it to come out to be a constant speed on that.
I wasn't either. First time I ever saw that problem, I was like, this can't be right. But it is. All right, this will be our last example. This is it for related rates, at least for what I'm going to show you. A sprinter runs around a circular track, which has a radius of 50 meters. She runs at a constant rate of 7 meters per second. Her friend is standing at a point 100 meters from the center of the track. How fast is the distance between the two changing when the two are exactly 120 meters apart? Okay. Picture time. I'm just going to start drawing a picture. I have someone running around a circular track. So I think I'm going to draw a circle. But I'm going to cheat because my circles suck. There we go. Okay, I have a circular track. This circular track has a fixed radius, right? 50 meters. Center of the circle out to any point is 50 meters. This person is running around this track at 7 meters per second. Now it doesn't say what direction, right? So I can make this person go running clockwise or counterclockwise. It does not matter. So which way do you want her to go? Clockwise or counterclockwise?
Counterclockwise.
Counter? Okay, we'll go counter. So here she is, that's her. And she is moving around this circle at a constant rate of 7 meters every second. Now it's a curved track, right? It's a curved track. She's moving at 7 meters per second around this track. Her friend is standing at a point 100 meters from the center of the track. So here's the center of the track. Her friend is somewhere, it doesn't tell you where, right? But they are 100 meters away from the center. So I can measure out 100 meters in any direction and put her friend. So just to be convenient here, I think I'm going to go out to the right. There's 50 meters, right? And then go another 50. Right there, there's her friend. That's 100 meters. So y'all understand that I can rotate this. It's the same picture, right? I do that, it's the same picture. It doesn't matter where her friend is. It's all the same. I'm just doing it horizontally for convenience. All right, those are fixed, right? The 100, this 100 is fixed. This 50 is fixed. We are interested in how fast the distance between the two is changing. Well, I need to draw that, don't I? We need to draw the distance between the two. That would be the distance going from this person to this person. Let's call that H. Right? So as this person moves around, that H changes, doesn't it? That H changes. It looks like you know what? I'll give it away. I don't want to give it away yet. There's my little runner. That can't be how fast she is because, yeah, no.
This isn't fast forward.
All right, but that's the picture, right? Moving around. So what do I want? I want to know how fast the distance between them is changing, right? I want dH dt. Is there a specific moment in time when I want that?
When H is equal to 120.
Yeah, when they're exactly 120 meters apart. So I want that exactly when they're when h is equal to 120. Hey, wait a minute, hold on a second. Is it possible for her to even be 120 meters away?
Yeah,
Yeah.
I
From here
mean,
to
on
here
the
is
if she's
100,
on the
right?
if she's on the far side, she's 150 meters away.
Yeah, here would be 150. So it would be somewhere in here, right?
Yeah,
Or
probably.
down here, right? Isn't there two different spaces or two different points on the other side of that circle where she would be 120 meters away?
Mhm.
So let's
There's
say
going
that
to be
we're
two
talking-
answers, isn't there?
Well, yeah, there could be two answers, but think about it. If she's right here, let's say she's right here and she's 120 meters away, is H growing or shrinking?
Growing.
Growing.
Growing because she's running this way, right? And then when she comes around like that, then she gets to 120 meters, but now H is shrinking, right?
Yeah.
So we're going to get like one answer, and it's either going to be positive or negative, but the magnitude of it will represent the speed that she's moving away or towards. All right, what are we given? Shoot, we're given something. We're given the speed she runs, right? 7 meters a second. And this is d something dt. D what though?
Is it dr?
R being what?
The rate?
The rate or rate? Are you saying rate or radius?
Oh no, I thought the constant rate was r.
Yeah, the radius is constant, right? So it's not, that doesn't, the 7 meters per second is not how fast the radius is changing. We have problems. Do you see we have a problem? Do y'all see that we have a problem? Like right now, I have no way of labeling this 7 meters per second because 7 meters per second is her. What
As their circumference.
Is that the change in circumference? Is the circumference of this circle changing? If the circumference changed, wouldn't it have to grow? The circle itself grow or shrink? If I change the circumference? And it's not, right? The circumference is fixed.
It's just change of her position. That's all it
It's
is.
just that her position, but can we label it? Like everything up to this point, we've been able to label, oh, it's just the distance from here to here. Or, oh, it's that line, or right? Like this is trouble. The trouble is because we have a curve. You can't call like this X. I think that's where you were getting circumference, right? This idea that that's changing. It's curved though. It's something is amiss here. All right, you ready? This is why this is the last example. I need to show this to you. So watch what I'm going to do. I'm going to go back to pre-cal. And I'm going to, instead of talking about her speed along the circle, okay, which we call in pre-cal your linear speed, we're going to try and convert this 7 meters per second from a linear speed to an angular speed, instead. So instead of measuring her speed around the track, we're going to measure the speed of her angle around as she goes around, right? Because when you look at this, right? When you look at this, as she goes around at a constant rate, oh, why is it stopping? That's really weird. As she goes around at a constant rate, her angle, the angle that she makes also goes around at a constant rate, isn't it? Like the second hand on a clock is constant. If you were to imagine like her being like a second hand or something, well, of course, time would be going backwards, but that's a different story. But you know, the idea is that it's constant, right? So can we do it? There's so many different ways to convert from linear speed to angular speed. There's formulas and all this other stuff. I like to just think it through. We want to know how long it takes her to go around the track. Okay, let's see. Can we figure out how much time it takes her to go around the track once? Well, she goes 7 meters per second, right?
Yeah.
Do we know the length of the track?
Not exactly, but we can find it. We
How?
have the radius.
We have the radius.
Our circumference, which would be 2 pi r.
Circumference of that circle would be 2 pi times the radius, right? And we know that the circumference, we know that the radius of this is 50. With me? So the circumference of this is 100 pi meters. I'm putting meters just so you understand, like we just measured the total distance around the circle. Circumference is 2 pi times the radius of the circle is 50. So I know the distance it would take, right? The distance around the whole thing. Now, how long will it take her to go around?
Would we want to just divide that by 7?
Yeah, divide it by 7, because she goes 7 meters every second, right? She goes 7 meters every second. So how long does it take her to go 100 pi meters? So the time it takes her should be equal to the circumference, the distance she travels, right? Meters over her speed, meters per second.
Sub 44.879.
I'm going to leave it. I'm going to leave it as an exact number. I'll get decimals later. I'm just going to say 100 pi over 7 seconds is how long it takes her. And what did you say that was about what as a decimal?
About, should I round it up because it's almost 45. It's 44.879.
87. Let's go 888. Okay.
Yeah.
Seconds. All right. So it takes her about 44.88 seconds to go around once. Y'all with me? To go around the track one time, one full revolution takes 48.88 seconds, or 100 pi over 7 seconds. So now I'd like for you to consider this. What is her angular speed? What is her change in angle with respect to time? So I need to draw her angle here. Imagine a dotted line connecting from the center of the circle to her and calling this angle right there theta. If I want to know how fast theta is changing with respect to time, then I need to know how much angle does she cover in how much time?
Covers 360 degrees in 44.88 seconds.
She covers 360 full degrees, right, in 44.88 seconds, right? Now, I'm not going to use degrees. I'm going to use radians. So she covers a full rotation is 2 pi, right? So she goes 2 pi in exactly how many seconds? 100 pi over 7. This is how many radians she does in this many seconds. One full rotation in 100 pi over 7 seconds is the same as 2 pi radians being covered in this many seconds. And some things are going to actually cancel out here. Do y'all see that? This is the same as 2 pi times 7 over 100 pi. Pi's cancel, 250. So we get an answer here, d theta dt is 7 over 50 radians per second. Okay, you need to take a step back and understand what we just did, because there's a lot going on here. You got a person running around a circular track at a certain speed. What we did is we said, okay, let's see how long it took her to do that. So we figured out how long's the track, figured out her speed, divided the length of the track by her speed, and that told us how many seconds it took her to go around once. And then we said, okay, well, if it took her that many seconds to go around once, then it means it took her that many seconds to do 2 pi radians of a revolution, which is this. And then you take that and you say, oh, well, that, if we divide, right, is just 7 over 50. That's how many radians she's rotating through every second. 7 over 50 radians per second is her change in theta over time. Now, I know you're sitting there and you're like, what the, okay? But we're actually now to a point where we can solve the problem, because our goal was to try and see if we could somehow relate these two together, and we couldn't figure out what to do here. But here's what we do know. D theta dt is 7/50, right? That we know. We were able to extrapolate that from this. And now I have theta in my picture. And so can I connect theta and h together?
Yeah, because
How?
that's a triangle technically.
It is a triangle.
So we could use probably one of or any of the cosine sine tangents would do it. I don't know which one, or if there's one that would be better if there's another one, but though any of those
Can we
would
though?
have them.
Can we use sine cosine tangent? Is this a right triangle?
No, you're right.
It's not a right
It's
triangle,
not a right
right?
triangle.
It's not a right triangle, but it is a triangle nonetheless, right?
Yeah, forgot those. They have to be right.
So yeah, so for sine cosine tangent, we have to have right triangles. So let me do this. Let me draw it for you again. We just have an arbitrary triangle. Right? Some arbitrary triangle here. This is theta. This is 100. This is h. Can you connect these together? Oh, sorry. This is what, 50? Sorry, I forgot that. Isn't this 50? Because that is, this blue here is this, right? This side is the gray, the distance from the observer to the center. And then h is this. 50 is fixed, agreed? As the angle changes, 50 never changes. This doesn't change, h does. Anything, any formulas you've ever seen in your life that somehow connect sides of triangles to angles of triangles?
Yeah,
I
it's,
don't
it's,
remember them.
it's
I
either
know we had
the
learned
it's
them.
either the laws of cosine or the laws of sines. One of them, right?
Good, yes, exactly. Let's go look. Here's the old trig formula sheet. You got all this stuff here. Here's law of sines, and here's law of cosines. So the way law of sines works is that in order to use it, you have to have two angles, or let's say an angle in its corresponding side and the other angle in corresponding side. Those are the things you're working with. So if we look back at this picture, where's my picture? You know what? Let me grab all this. No, stop. No, let me grab all of this. This is like the Widowmaker problem, you know? There's a lot going on here, right? If you can do a problem like this, then you're in good shape. All right, so here we go. If we have an arbitrary triangle, law of sines, let's see what law of sines would relate together. It would relate this, this, with this, and this. So you'd have to be looking at an angle in the opposite side and another angle on the opposite side. I have an angle on the opposite side, but I don't have another angle, do I? I only have one angle out of the three. So I probably don't want to use the law of sines. Law of cosines, let's see, what does law of cosines involve? It involves all three sides and just one of the angles. Sorry, the BC is here. So BC, A, and the angle A. Don't we have this? Don't we have three sides and an angle? Now, we don't know what H is. We don't know what theta is, but we have a relationship. If I were to label this triangle over here A, and then call this one B, and then call that angle C, that would make this little a, this would make this little b, and this would make that little c. And then I could use law of cosines. I would have a squared equals b squared plus c squared minus 2bc cosine a. What's a for us?
Theta.
What's A? A is.
Oh, that A, H.
Little a, sorry. So using this formula, I would have little h squared equals, okay, b squared. B is 50, so 50 squared. Plus c squared, c for us is 100 squared, minus 2 times, all right, b, which was 50, c, which was 100, cosine of A, and A for us is the angle theta, capital A. There it is. That is an equation that connects theta and H together. So all I have to do is differentiate it, and I'm in business. Daniel, are you shaking your head, Daniel? You're the one who came up with the law of cosines. Why are you shaking your head? Is it all the other stuff leading up to it?
This problem is just so goddamn complex.
It is. It is. All right, I'm ready to differentiate. Okay, that's my equation. I'm gonna differentiate. I'm not gonna do anything. I'm just gonna, here we go. Derivative of that is 2h dh dt equals, oh, this is nice. What's derivative of 50 squared?
It's 0, isn't it?
0 plus 100
Zero.
squared, 0. Okay, everything else here is constant, -2, 50, 100. Those are all attached to the cosine, so they're going to come for the ride. What's derivative of cosine theta?
Negative
My-
sine theta, right?
Negative sine theta. Drum roll.
Times theta, derivative of theta over the derivative of time.
D theta dt. Do not forget the chain rule, right? Derivative cosine of theta is negative sine theta, d theta dt. And we have it. We have it. We have everything we need. dh dt, that's what I'm looking for. D theta dt, we had to extrapolate that, but we found it 5 over, what was it, 5 over 70? Something like that. There's still 2 things you don't know though, h and theta. Well, do you know h? Hold on, take that back. Didn't we know h at the moment in time?
We
Yeah,
do.
it's 120.
Yeah, 120, right? So I can replace this with 120. So I'm actually really cranking now. That's going to be replaced with 120. The only thing I don't know is theta. But can you get theta? How can you get theta? You can fix everything now, right? Can't you fix everything?
Yeah, we could fix it and then we could use, yeah,
You can fix h now. H is 120. So this is 120 squared equals 50 squared plus 100 squared minus 2 times 50 times 100 times cosine of theta. And these are all numbers you can solve for theta. You'll have to come in with an inverse cosine function to do it. Dot, dot, dot. I'm not going to finish this. I'm going to just leave this to you. Now it's just a matter of plugging things in. I'm not finishing it on purpose, all right? Because I want to see if anyone will go do it on their own. All right. Goodbye, related rates. It's over. It was nice. It was fun. I told you when we first started, we could spend, you know, an entire semester doing related rates. I mean, we really could. All right. Congratulations. You've made it to this point at least. All right. Now we get to shift gears. All right. We get to shift gears a little bit, which is good. So let me look at our schedule, see where we are here. So I told you before that we would try and cover as much of this in one shot as we could. Today is the 26th, so yeah, we're good. Why don't we do this? I'm gonna go refill my drink. Just take 30 seconds to just clear your minds. We're gonna take a huge step back now, okay? A huge step back and start something that I think will be refreshing. I hope it'll be refreshing. So let's just take 30 seconds, go throw up in the toilet or something. All right. So when I was in graduate school, the college hired me to be a teaching assistant, and we could do one of two things. We could become tutors at the university tutoring lab, in the math tutoring lab, or we could also become what are called Calculus 1 recitation instructors. So in most major universities, when you take calculus, you go to lecture twice a week. And then once a week, you meet in a room with students, with your classmates, and they have some graduate student who stands up in front of the class and is like, any questions? You know, and basically you can ask questions about homework problems, whatever. And I can remember my first time ever doing that. I was so scared because I knew people would be asking about related rates. And you have to be pretty damn comfortable with a lot of stuff to be able to just answer random related rate problems. Because it's one thing to like teach the chain rule or the product rule or the quotient rule. That's very mechanical. But when it comes to related rates, I mean, you got to feel real good about a lot of geometry and stuff like that. It's pretty terrifying. So I can say that when I finished Cal 1, I was nowhere even close to being decent at related rates. I mean, I was just okay. I mean, it took years and years and years and years and years of practice and practice. And I know for a lot of you, you probably won't see related rates ever again. You probably are going to move on, do engineering, computer science. Only really like math majors are going to do more. So the big takeaway from related rates is that they should make you feel really, really insignificant. Like related rate problems should make you feel like, wow, there's this huge like universe of complicated problems that you're not quite ready for. But this is supposed to get you starting to feel that sensation of this is the way the real world works. There's problems, there's not a set path of how to get to the solution. And that's what your college degree is supposed to mean. It's supposed to mean that you have become a pretty decent problem solver. Critical thinking, problem solving, not giving up, right? Persistence. You know, you can't just say, I hate related rate problems. I'm just gonna, you know, you have to want to do it. You know, there has to be that desire, like, I'm gonna get this answer, you know, I'm gonna get it. So that's kind of the big picture. We move on. All right, we're going to move into the next chapter. All right, congratulations. We're out of chapter 3. I mean, out of chapter 2. We now start chapter 3. So I'm going to skip over 3.1 and 3.2. 3.1 and 3.2 is just a review of exponential and logarithmic functions. All right, it's just a review. Now, when I say skip through, I am going to talk about it, but I'm going to go so fast through it. It's going to take us like 5 minutes. So if at any point I say something and you're like, I don't remember that, or you may want to go back and review this stuff. Okay, here we go. All these notes are online. So let me make this a little smaller. All right, exponential functions, we're gonna start with that. So you should have learned that in what, college algebra, right? That's where you see this. You should have learned in college algebra about this function called an exponential function, where you have f of x equals a to the x, a number raised to the x, not x raised to a number, not x squared or x cubed. This is a number raised to x. Now, these are called exponential functions. The a here is called the base of the function. And we have a condition that that a has to be positive and it can't be 1. So to define an exponential function, we have to have a positive number down here and it can't be the number 1. And then what you should have learned is that the graphs of these are going to look like one of two things. It's either going to look like this, which we would call this graph goes like this, and then it has a horizontal asymptote. We call this exponential growth. Exponential growth happens whenever a is bigger than 1. So if your base is ever a number bigger than 1, then you're going to have this sort of growth. What we want to do is look at it from the perspective of calculus now. If I ask you to look at this function and tell me what the limit is as x goes to infinity, you would say, okay, well, as I go to the right, to infinity, the function is taking off to infinity, right? So with exponential growth, the limit as x goes to infinity of the function is infinity. Now, if I say, look at the limit as you go to the left, now the function is descending down and asymptotically approaching 0, never getting there, right? Headed to 0. So the limit is, the y value is headed to 0. Does that make sense? Out to the right, heads to infinity, out to the left, goes to 0, as long as it's exponential growth. Now, if you have exponential decay, it's the other way around. It looks like this. And this happens whenever the a is what? Not bigger than 1, but what?
Less than 1.
1.
The a has to be between 0 and 1 for you to have decay, exponential decay. So it goes, it's the opposite of what we just saw. As you go out to infinity, this way, the function dives down and heads asymptotically to 0. If you go to negative infinity, this heads up to positive infinity. And so these kind of switch places compared to the exponential growth. Right? All right, we move on. Properties of exponents from college algebra. We already know these. If you have a to something times a to the something, you add the powers. If it's division, you subtract. Something to a power, all of that to a power, you multiply. And if you have the product of two things to a power, you can put the power on each one. These are all exponent properties, so I'm not going to go through those. That's it. That's all I'm going to say about exponential functions. Okay. Logarithmic functions. So when you have a function that's a logarithmic function, all logarithmic functions look like this, where the a is the base. And these log functions have graphs. And this is the graph of a log function if the a is bigger than 1. This is what a log function looks like. All log functions will look like this as long as the a is bigger than 1. So let's talk about the limits. As x goes to infinity, so as we go out this way, what is the function doing? Where's it headed?
Looks to be approaching infinity.
It's slow growth, right? Naturally,
Yeah.
the log functions continue to grow. It's definitely not like an exponential where it just takes off. It's very slowly growing, but it does grow forever. So that does very slowly head off towards infinity. So that's what this says. Now with the log function, I cannot go to negative infinity. Why? Why am I not allowed to go out to the left?
Because there's a vertical asymptote over there.
That's right, there's a vertical asymptote. You cannot plug negative numbers into logs. College algebra, logarithmic functions have domain restrictions. You are never allowed to plug in 0 or negatives into logarithms, which means that when you look at the graph of any logarithm, it will never exist to the left of the y-axis. So we can't talk about the limit as we go to negative infinity. What we can talk about is the limit as we approach 0 from the right. So as we head towards 0 from the right-hand side, where does the function go?
Negative infinity.
Negative infinity. It dives down forever, right? That's what that second limit there says. Questions? What happens if the base is between 0 and 1? Picture changes, becomes that one. So look at the limits. As we go out to the right to infinity, the function starts going this way forever and ever and ever. And it's headed towards negative infinity. Oh, by the way, this is if the base is between 1 and 0. And then as we head towards 0 from the right, again, we can't go past 0. We got to just get closer. Then at this point, this function heads up to positive infinity. So that's what these two things are saying. Okay. What are the two most important logarithms that we use in like everyday life that you've seen and heard of?
E.
E is
Euler's number?
exponential. What's the inverse of the E function? Remember, exponential functions and logarithmic functions are inverses of one another. They undo each other. They
Is
kill
it
each other off.
ln?
ln.
log.
Natural log. The natural log of x. The natural log. That is something you should have seen in college algebra. At the end of the day, that is simply a log function. Okay, but what is the base of the natural log function? Who knows what the base of it is? What the base of
Was
the
it 10?
that's the other special one.
Would that be base E?
That's base E. Whenever the base of the log is E, you get the natural log function.
Well, real fast, what was like? What was E again? Wasn't it like a pi-like number where it was like
It is. It's
some
an irrational
horrifically long
number.
decimal?
Yep, it's an irrational number. I'm actually going to talk to you about it in just a minute if I have time. I think I will.
Okay.
So the natural log function is just a log function base E. That's all it is. It really drives me crazy because look, when you're learning about logs, they give you this general form, like this is what all logs look like, and they tell you that this number is the base. And then they say, okay, but then there's this special one, natural log. And all students seem to forget that the base is just E. And it frustrates me because like, I wish we would have never used that notation. I just wish we would have just stuck with this notation because it shows you the base in the notation. The reason that we did that and went to this notation is purely historical, goes back to when typewriters were being used. And it was a real pain in the ass on a typewriter to do subscripting because you'd have to type and turn the drum, hit a key, turn it back, and it was really slow. And so we said, well, if you just do it, if instead of doing this, just do this, then you don't have to stop typing. And so it made things much faster. But in it, we lost, students don't realize that it's just a log function base E. All right.
So
the other important one, go ahead.
I just have a question. It's been a real long time since I've touched logarithms. The conversion on that, the base, that is the conversion on that. If it's log E of X, that would be the inverse of X to the power of E, correct? Or is it the other way around?
Say it again.
Like log E of X, that would be the inverse or the undoing of X to the power of E,
I'm going to
correct?
show you. It's
Okay,
It's
good.
the inverse of E to the X.
Yeah, it's the
Is that what it
inverse of
was?
E.
Yeah,
Yes.
it's I remember natural log being a thing, and I remember base 10 being important, but I don't remember how to actually do logs at all. So
Okay. Well, right now, I just want you to understand that the natural log function is just one specific example of a log function where the base is e. The question has been posed, what's e? Get to that in a minute. Log, just log, without anything written under it, is understood to be log base 10. So again, this is another one of those notations where it's like, man, why don't we just put the 10 there? Because it's easier to type that, all right? Now these bases, E and 10, the reason why they're important, I'm about to explain why E is so important. I'm about to explain it to you. All right, it's going to hopefully blow your mind. The reason why base 10 is important is because our number system is base 10, right? 10 fingers. That's why our number system is base 10, because we have 10 fingers. That's the way we count. Okay, if we had 8 fingers, we'd probably be using base 8. And if we had 16 fingers, we'd probably use base 16. That's another conversation for another day, all right? But these are the most important logarithms that we use. And so these are the ones that have special notation for them. All other logs, you explicitly have to write what the base is, all right? Okay, properties of logs, college algebra. If you ever take the log and you have a product inside the log, you can split it into 2 logs. This was called expanding and condensing log expressions. If you have a single log with division inside, it can turn into 2 logs with subtraction. This is a big property right here. We're going to use this big time. If you have any log of x raised to the r, you are allowed to pull the r out in front. Very important. All right. So when we're talking about exponential functions, the previous section, exponential functions, there is a very special function, not log function, exponential function. There's this very special function, e to the x. E to the x. That is basically an exponential function where that base is this special number e, right? And it is known as the natural exponential function. When we put that same e in the base of a log function, we get the natural log of x, right? These two are inverse functions. So if we think about a function like a machine, whatever this function does, this function undoes it. Whatever this function does, this function undoes it. So if this takes a number and turns it into a new number, this will take it right back to where it came from, and vice versa. So we have these properties. This is what I think Hunter was asking. If you take natural log and inside of it, you put its inverse function, e to the x, then they kill each other off and x pops out. I like to look at it this way. If you start out with x here and you send it through the e to the x function, it's going to come out as a number. The natural log function takes that number and sends it back to where it came from. Okay. It works the other way around too. If you take an x and plug it into the natural log first, and then put that and raise e to that power, it sends it back and kicks x back out. So that would look like this. If we start with the number x here, send it through the natural log function, it comes out as a number, e is going to take it right back to x. Other properties, e to the 0 is 1. Any number to the 0 is 1. We should know that, except 0. 0 to the 0 is undefined. Natural log of 1 is 0. The natural log of 1 is 0. That you can get from the graph. If you look at all these any logarithmic function, doesn't matter which one it is, all logarithmic functions pass through this point, 1, 0. The natural log of 1 is 0. The natural log of 1 is 0, right? The natural log of 1 is 0. All right. The natural log of e is 1. This fifth property is actually just this property, replace x with 1. and you get 1. So natural log of e to the first power is the same as natural log of e, and so natural log of e is 1. All right, we keep going. This is all review. There was a very important formula in college algebra called the change of base formula. If you look at a key, most calculators only have a natural log key. Some of them have a log and a natural log key. You really can survive with just one. All you need is one. And the reason you only need one is because this formula right here. If you want to figure out the log of anything, any base, doesn't matter what it is, you can, as long as you have a natural log function or a natural log key on your calculator, you can figure out what it is. Review. All right, we're ready. I have 10 minutes. So we're just gonna barely get into this. All right, so if you need to, on your own time, go back. I mean, you all passed college algebra, right? So at some point you did kind of understand this. If you need to, take some time to go back and review. The textbook has an entire section, 3.1 and 3.2. You can open up your ebook and you can read through it and see, you know, how much of that makes sense to you. I'm skipping over that though. So I'm going straight to 3.3 now. Derivatives of the log and exponential functions. We have conveniently avoided these. If you go back and look at everything, we can take derivatives of all sorts of crazy functions, right? Sine and cosines and tangents and square roots and all these crazy things, chain rule, product rule, pretty crazy functions we can take derivative of. But right now we have stayed away from exponential and log, all right? We have stayed away. And we did it for a reason, all right? But let's get to it. So I was asked about E, right? E, this number, right? It's approximately 2.718. And it's like pi, it keeps going, never has a pattern, goes forever. It's a very special number. It's so special that when we use that as the base of a log function, it's called the natural log. And when it's the base of the exponential function, we call that the natural exponential function. Natural, you've heard these words before, natural log, right? Natural log, natural log. Have you ever wondered why they call it natural log? What's natural about it, right? What's natural? What does natural mean? I don't know. I mean, like the sun.
Innate to nature.
Yeah, like the sun comes up. We're all familiar with the sun, right? Maybe we can't explain it, but it's natural. It's a natural phenomenon that we see, right? It's just, it's there. It is the way it is, right? This E, there's some natural element or aspect to it. It's easy to explain once I just shut up and explain it. So here's the conundrum that we had. Okay, we meaning humans. We started to figure out, okay, taking derivatives is all about finding the slope of the tangent line, right? So if we take a function, let's say we take the function f of x equals x squared. We can look at its graph, right? And if I go out to, let's say 1 on the graph, that'll be this point 1, right? What is the slope of the tangent line there? If I draw a tangent line right here, what is its slope?
2x.
Well,
No.
the derivative of that is 2x, right? So the derivative of this
Yeah.
is 2x. And
So
so
it'd just
now
be
if I
2.
wanted to know the slope of the tangent line at 1, you would just plug 1 in here and you would tell me the slope is 2, right? Slope of that is 2. Because you plug 1 into the derivative, yes? Okay, and if I went and take the same function, x squared, and now I ask you to go out to 2, or let's go to 3. If I say go to 3, where will you be here? 3 squared is 9, right? What's the slope of the tangent line here?
6.
Take the derivative, plug 3 in, you get 6, right? Everyone with me? Everyone good? Everyone understand what we're doing here? Let's do one more of these with the same function. X squared, same thing. Let's go to 2. If I plug 2 in, what do I get? What's the point here? Plug in 2, you get 2 squared.
4.
4. Everyone good? What's the slope of the tangent line here?
4.
You're getting that by plugging 2 into this, right?
Yeah,
Okay, so you get 4. Hey, wait a minute, hold on. These were the same. Those were the same. The y value here happened to be the same as the derivative there, right? Was that a coincidence?
I'm assuming since you're pointing it out, it isn't.
Well, for this function it is, right? Because look, here it was 2 and here it was 1. Those weren't the same, right? Here it was 6 and here it was 9. Those weren't the same, right? But here on this one, at this one particular point, the slope of the tangent line is equal to the y value of the coordinate at that point, isn't it? But it seems like at other places it's not. So mathematicians and physicists and other scientists were asked this question: is there a function where this happens everywhere on the function,
I knew you were.
where the slope of the tangent line
Oh,
is
man.
always the y value? Always, no matter where you go. And we went looked for it. We tried to figure out, is there anything that does that? Is there anything that does that? Is there anything that does that? And voila, out of nowhere, not out of nowhere, but we had to go hunt for it, okay? We said it does work. There's this one function that behaves that way, and it's the only one that does it. It's the only function that has this property. And it is, we can't explain why it is this way, but it is this e to the x. That function behaves that way, uniquely. Nothing else does it. So if you take the graph of e to the x and you graph it, well, let's do it nice. Let's do a real graph. If we do e to the x, okay, there it is. Now I will point out, this is, let's say that's e to the x. This is 2 to the x. These are two different functions, right? I'm not talking about any exponential function. I'm talking about I almost said Mac Daddy, the biggest one, the e to the x, the guy, all right? This one behaves in this manner. If I go to any point, so let me go to a random point here, m, e raised to the m, add slider. So if I take any point on this curve right here, okay? Let me label the point so you can see it. See that? That's the point here. If I go to any point here, right there, let's say I go right there and I ask it for the slope of the tangent line, what is it?
5.474.
5.474. That's the slope of tangent line. The slope of the tangent line, that slope, m, is actually equal to that value. These are the same. Everywhere on the curve, it's like that. Everywhere. You don't believe it, go here. What does the slope of tangent line look like it is here?
1.
1. What's that point?
1.
0, 1. Oh, that's what's happening. Everywhere on the curve. Which means this. If you want to know what the derivative of e to the x is, it should be what?
Should be equal to
X.
y.
E itself.
Yeah.
Right? Itself. It is the derivative of e to the x is itself. That's what it is. If you change this number at all to a different number, this doesn't work. So again, we call it the natural exponential function. We call e the natural base because we can't really explain to you why this is the number that works, other than that's just the way the universe works, all right? That's the one, that's the number that does it. Anything else? Doesn't do it. So, yeah.
Well, I was just going to ask, I mean, you maybe about to jump into it, but log, does it do the same thing, or is it the natural log simply because it is the inverse of the natural exponential?
The natural log is called the natural log only because it is the inverse of this function. It does not have the same property in terms of the derivative. Okay, it does not. This is the only function, right? This is the only function that is its own derivative. All right, I'm out of time, so we are where we are. Excuse me. We will pick up, don't do any homework from 3.3. We haven't even talked about it. This was just to get you to kind of see where this all comes from, like the big question, right? So your homework would be more related rates. Make sure you finish it all. And if you're finished and twiddling your thumbs, you should probably go and look at 3.1 and 3.2 and review some of the properties of logs, graphs of logs, things like that. Look through the book, the ebook, and see what types of things it's asking for. I do not believe I have any solution videos for any homework out of those sections. Any questions?
What all is going to be on this next test?
I think everything, well, when's the test? Tuesday?
Yes,
Is it Tuesday? Well,
November 4th.
I will say up through related rates, maybe some stuff from Thursday. I think if I show you the stuff on Thursday, I'll ask the class, do y'all want this on the test? You may want it on the test because it's much easier than other things.
I don't expect it to be harder than related rates.
Yeah, it won't be. There's only one other area in this class that gets as messy as related rates, and that's optimization problems. And that's again because they're word problems, but those come at the very end. So
Are we
got
going to get a
some-
review for this test?
I'm going to put something together.
The exam is next Thursday.
Is it Thursday?
Mhm.
I need to look.
Okay, I said
I
you.
thought I had switched it. Hold on. No, yeah, November 4th, right? That's right.
Mm.
That's what we're shooting for. Yeah, I would love to be able to put 3.3 on this test. I think it would make sense to have it on this test. And then that would leave us L'Hopital's rule in chapter 4, basically for the final. Oh my gosh, is this real? 1, 2, 3, 4, 5, 6, 7, 8. We only had 8 more class meetings. Well, got a lot to do.
Isn't the L'Hopital? That's
Y'all
like
free to
French
go.
or something. That one's. I was talking to a friend who is